Hello everyone. This lesson we're going to talking about the neutral current in an unbalanced three-phase 4-wire system. So first we're going to show you what's defined as a neutral. I have a three-phase panel down here. Have A, B, C and the neutral in this panel. If I pull all three lines connect onto the load and I have a white conductor connect to common of those three loads, this conductor we define as neutral conductor. Another one, it's pretty common in high-rise residential construction. For a high-rise residential tower, you will have three-phase panel in there, but into each unit, we pull two lines with a white conductor. So in this case, we have a line A and a line B and a white conductor. That white conductor, we cannot call them neutral anymore. That one will become a common conductor. The definition for the neutral conductor is only carry unbalanced current. But for this common conductor, even it's a white, it's not carrying the unbalanced current. It actually carries the full current compared to the line conductor. The third one here, we have a single phase load. We pull a hot conductor and a white conductor down here. This white conductor, even on the job site, we usually call them the neutral conductor. But in here, this is called identified conductor. This identified conductor carries the same amount of current as your line conductor. So we have to understand which one is considered a neutral conductor in a system. I can give you a summary. In three-phase 4-wire, if the white conductor is common to all three-phase load, then that's a neutral conductor. And in single-phase 3-wire, you learned in year 1, the single-phase 3-wire, that's a neutral conductor. Other than that, all the white conductor is not the neutral conductor. So now we understand the neutral conductor, we can do our three-phase neutral conductor calculation. So far, we do the three-phase calculation, we all did is balance the three-phase load. When talking about balance the three-phase load, is the load in each phase has the same impedance and has the same power factor. So in short, they will have the same Z and the same PF. PF is the power factor, Z is impedance. Only when all three loads have the same impedance and the same power factor, they will consider as balanced load. But a lot of time in the real world, we're going to dealing with unbalanced load. We have an unbalanced load, the neutral going to carry a current. This time we're going to show you how to calculate that neutral current. I have an example down here of three-phase 4-wire supply, line A, line B, line C with neutral. I have three loads connected in Y configuration. This probably your first time saw I draw the Y configuration down here, but you can see all three loads have a common point connect together. They connect onto the neutral conductor. So one phase have 60 ohm, another phase have 30 ohm, the third phase have 20 ohm. Supply is 120, 208, three-phase. So I know my line voltage is 208 volts, phase voltage is 120 volts. I can calculate each phase current by using the phase voltage divided by the phase resistance. I have 2 amp at 0 degree, 4 amp at 240 degree, and 6 amp at 120 degree. the neutral going to carry the unbalanced current. So the neutral current is a vector going to equal to the three-phase current, the vector add up. I have a circle drawing down here. If I have a balanced load, which means all those three currents going to be the same because they have the same impedance, same power factor. They're going to be 120 degrees apart. So when those are three, the equal length, I draw a circle around there. I can see they are touching the edge of the circle. In this case, my neutral current is going to be equal to 0 amps. But like the sample I gave to you, this time we don't have balanced circuit. So each phase will have a different phase current. We have resistive load, so they still going to have 120 degrees apart. Now here's my phase A, phase B, phase C. I draw a circle as the shortest one or the lowest current. It's 2 amp down here. My phase B we have 4 amp, so it will be slightly longer than outside the circle. My phase C we have much more higher current, so the phase C current will be higher. If I add all three vectors together, I will get 3.46 amp at 150 degrees. So we don't care about the degree, but we know the neutral conductor at this moment going to carry 3.46 amps. So this way to calculate the neutral current, we can use this circle. We can subtract the lowest one. We have a 2 amp down here at the 240 degree. We have 4 amp down here at the 120 degree. We could just add in these two vectors together to get the same number. You can see the neutral current down here is higher than the lowest current, but lower than the highest current. So when you do this neutral current calculation, if your current value is between these two values, you know you did the right calculation. If somehow you calculate this current the higher than 4 amp or lower than 2 amp in this sample, you did something wrong. We're going to show you something more in next lesson. If you have a question, you can connect us online and send us emails.